finish up the lens notes page. We left off about halfway through. So let me just redraw this diagram so you can remember how to draw these ray diagrams. Very, very top, the three rules say you draw the ray from the top of the object parallel to the axis. So I'm drawing it straight parallel to the axis. As soon as it gets to the lens, the thing focuses straight to the focal point. So I'm going to draw it down straight through like this, so this arrow comes like that. I should be drawing with these in straight lines, but for the sake of time, I'm just drawing it straight through. Number 2 says draw it straight to the center of the lens, and it just keeps going. So I have this one come down similar to that. Just keep going like that. And then the last one goes through the focal point on the left-hand side, something like this. And then as soon as it hits the lens, it goes parallel to the axis and then so it's the exact opposite of the first one. You notice that all three intersect. So you're going to see an image in the lens on the other side that is upside down. But the top of this one over here ends up being down here where they all intersect. So you'll see an upside down arrow. And we got through the first part by saying that formula of 1 over the distance object plus 1 over the image distance, the object distance, the image distance, equals 1 over the focal length. And so we put in the numbers we had of 1 over 30. And we were trying to figure out where the image was going to be, so I'm looking for my image distance. The focal length was 10. And so I'm going to subtract 1 over 30 from both sides. And that means that 1 over my image distance is now 1 over 30. 1 over 10 minus 1 over 30. You've got to find a common denominator, so that means that 3 over 30 minus 1 over 30 is now equal to 1 over my image distance, which is 2 over 30. Actually, it's a negative 2 over 30. And then you flip it. Oh, it's not a negative 2, I'm sorry. I was wrong there. It's a positive 2. You flip it over, and that gives you an image distance of 15 centimeters. And since it's positive, that means it's going to be real. We can actually project it on the screen. We then did the magnification. Magnification was a negative image distance, or die over dou. And so once again, we put in the negative 15 that I got from down here. Just took this, put it right up there. Divided it by the object distance, which was 30, that was given to us in the formula, and you get a negative 2, or I'm sorry, negative 1/2. That means it's going to be upside down, so the negative means upside down. We also call that inverted. And since it's 1/2, 1/2 means it's smaller. Now what's going to happen, they want you to do the same thing, but they want you to repeat this for the 10th centimeter and the 5 centimeter objects. So I'm just going to make my object distance farther away now. So I'm going to use the same formula that I did up here. Just going to change my object distance. So watch what happens here. I'm going to do 1 over di equals. Now my object distance is now going to be I'm going to go ahead and I just rewrote the formula so I don't get ahead of myself here. So the object distance now is going to be 10. I'm going to put 1 over 10. My image distance is what I'm trying to find. And my focal length is still 10. Well, look at this. If you subtract 1/10 from both sides, so now 1 over di equals 1 over 10 minus 1 over 10, you get 0. So therefore, you will get no distance, so the inverse of 0 is infinity. So you will get no object whatsoever. You can never ever see it. So anytime you place the object at the focal length, your image distance is infinity or 0. And since there's no image, you can't get a magnification either. Last thing on that list, let's make our object now 5 centimeters away. So we'll do the same exact formula again. 1 over do plus 1 over di equals 1 over f. And so I'm going to put in 1 over 5 plus 1 over di equals 1 over 10. The focal length is 10. I'm going to subtract 1/5 from both sides, so 1 over di now equals 1 over 10 minus 1 over 5. Find a common denominator, you get 1 over 10 minus 2 over 10. That gives you a negative 1 over 10. Now when you flip it, that ends up giving you a negative 10. So the distance image is negative 10. Well, here's what that means. That means it's virtual, which means it's back in the mirror. You can't really put it on a screen. Now they also want you to find the magnification. The magnification is going to be equal to negative di over dou. So I take my image distance of a negative 10, divide that by the object distance of 5. And so now you get a positive 2. So that means the image is now upright, standing upright, and it is 2 times bigger. 2 times bigger. Let's do this last one here. Okay, on this last one here, I want you to be sort of careful, because if you follow your rules on the lens here, you're supposed to go parallel to the lens, and it's supposed to go through the focal point. Well, since it's a diverging lens, that means the ray is going to actually diverge and go out like that. So the ray actually comes backwards through this focal point. And it doesn't really ever do that, okay? The X one would go straight to the center of the lens, so it would come back something like this. Okay? And then the other one would go straight through the focal point on this side, and then bounce off parallel to the lens like so. Okay? So if you notice, there is no point where all these rays meet at all. Okay? So the focal point is actually negative because it's on the back side of the lens. It's not over here. This is the front part of the lens. Okay? It comes in the side and then goes on the front. So since there is no focal point, you're not going to get any type of image that happens in the back of the lens. So we call this a negative focal point now. So our formula is going to be a little bit different when we start figuring out what these object and images distance are. We're going to put in the same exact formula, but watch what we do to the focal length. I'm going to do the same numbers as we had before. So I'm going to put in a object distance of 30. The image distance is what we're trying to find. But the focal length, since it's a diverging lens, has to be negative. So I'm going to put 1 over a negative 10. When we now figure out the image distance, I'm going to put in negative 3 over 30 minus 1 over 30 and so it gives you a negative 4 over 30. So we did all the math like that. And then we flip-flop it around. So now my image distance is a negative 7.5, which means it's actually over here. So it's going to be on this side of the mirror, and it's virtual. You cannot project that onto a screen. So you'd have to look at the thing through this side. Here's your eyeball over here, okay? And you'd have to look through it from this side to actually see the image. The magnification, same way we did before. Magnification equals negative di over dou. So I'm going to put in my negative 7.5. Divide that by my object distance of 30. And you end up getting a magnification that's absolutely huge. I'm sorry, small rather, of 0.25. It's about 1/4 of the height that you normally see it. So it's upright because it's positive, but it's also very, very, very small. So about 1/4 of the size. Now you're going to do the same thing, but now we're going to start moving the image back to the focal point. So we do the same exact formula as we did before. So I'm going to take now, instead of 1 over 30, I'm going to take 1 over 10 plus 1 over the image distance equals 1 over a negative 10, because the focal length, once again, is behind the mirrors. That's why this one's negative. It's up here. So now when I add something, though, I do end up getting a number of negative 2 over 10. And when you flip-flop it, that means your image distance now is a negative 5. Again, it's virtual because it's behind the meter. When you do your magnification again, magnification is negative di over dou. And so that ends up giving you a negative 5 over 10. And so now you moved your image up, but it just got a little bit bigger, but it's still upright. So it's upright. It's smaller. It's not as small as it was because now your magnification ends up being a positive 0.5. Finally, you're going to move it up to where it's only 5 centimeters away from the image now. The object is only 5 centimeters away. So I'm going to have 1 over 5 plus my image distance equals focal length of 1 over 10. Remember, it's a negative 10 because the focal length is in the back. So I flip-flop it around. So now I got 1 over image distance equals a negative 1 over 10 plus minus, not plus, but minus a 2 over 10. That ends up giving me a negative 3 over 10. So now my image distance, if you flip-flop it, is 10 divided by 3, or a negative 3.33. So now you will once again see a virtual image. Get you closer. And the magnification is negative di over dou. So I'm going to take that negative 3.33, divide that by my object distance of 5, and now you get a horrible number of a positive 0.666. So therefore, it is, once again, upright, and just a teeny, 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 weeny little slide. That's all I got to say about that. So there are your Lens notes. Hope you have a great day.